Hello everybody, thanks for dropping in on my talk. My name's Guy Davidson. I'm the Head of Engineering Practice at Creative Assembly. I've been there since 1993. I am delighted and proud to work there, and of course we're always recruiting. You can find me at HackCat01 on Twitter. Do drop by for peculiar texts about music and of course C++ programming. I'm the chair of BSI IST/5. This is the mirror group of SC22 for ISO. I'm effectively the chair of programming languages in the UK. I'm also a member of BSI IST/5/-21, which is the C++ panel for BSI. I'm a voting member of ISO/IEC JTC1/SC22/WG21, which you might know as the C++ Standards Committee. I'm also a member of BAFTA, the games we make, Total War. Have indeed won BAFTAs, which makes me eligible to become a member of BAFTA. That was nice. I get to hang out in a club in London. I'm also on the advisory board of IGI. IGI stands for Intelligent Games and Gaming Intelligence. And it's a postdoctoral research program on AI in games, really. I'm also a STEM ambassador. I do drop-ins and visits to schools and colleges and universities and try to persuade young people to become engineers and to pursue a career in the sciences. I'm the co-founder of Hash Includes. This is the diversity and inclusion group dedicated to improving the diversity of the C++ community. We're a bit white and a bit male, and we have a lot of problems that need solving and not enough people to solve them. Please consider dropping by and seeing if you can help. I'm also a Code of Conduct hobbyist. I was the Code of Conduct representative at CppOnSea, but also ACCU, CPP North, CppCon, Meeting C++. It's something I do care about. So, if you see me at a conference, I'm there to do Code of Conduct, I expect. I'm also a husband and a father and a singer. I sing with the Brighton Festival Chorus. I'm a musician. I play the piano. I have been an actor and a director on stage. I like cooking. I like living well. And I wear a beard. I'm also a cartoplect. You might not know what one of those is. You'll find out shortly. And I also wrote this book. I'm the co-author of Beautiful C++. Kate and I are taking it in turns to say how much the other did and how little they did. And Kate raised it up a notch at ACCU this year. She said that I wrote the book, but without her, there would have been no book. She devised it, reviewed it, gave close editing and commentary, cheered me on and showed me that there is a lot more to writing a book than writing the words. And Björn quite liked it as well. We got some blurb from him, and he wrote a foreword for us, and Herbsutter wrote an afterward. I love this book, and I'm very proud of it. Perhaps you'd like to read it. So here's our agenda. We're going to look at the nature of abstraction, and then some C++ features that support abstraction, followed by the art of working at the correct level of abstraction, which is critical to all of this. Then we'll look at some bad API design and some better API design. And there is some bonus content. Now, this is a recording, so I imagine I will show you the bonus content, but I ran out of time at the live version in Folkestone. So let's look at the nature of abstraction first. And I'm going to start with a little etymology. I asked a bunch of folk what they understood by the word abstraction and got a big pile of rather varied answers. The Latin root of the word is trahere, which means to drag or pull, and it gives us words like tractor. It also gives us the word subtract, literally to pull under, but more meaningfully to take from, as well as retract, to pull back, for example, to retract a statement. And we have contract or contract, which is to drag or draw together, for example, drawing together two parties in agreement. And we have extract, to draw out. Extract and retract may seem quite similar, and one of the confusions we have is the precise use of the prefixes. And when we come to abstract, which means to draw off from or draw away from, we might be grasping for a meaningful understanding of the word. Worse still, the word abstract can be a noun or an adjective or a verb. Looking at nouns, an abstract can be a summary of a longer publication. It can be a theoretical way of looking at things, something that exists only in an idealized form. Used as an adjective, it can mean conceptual or ideal, and it can also mean difficult to understand. Used as a verb, it means to summarize or extract by means of distillation, or to produce an abstraction. After writing this presentation, I was left with the notion that to abstract means to form a conceptual summary. So here's a word, plectere. It means to fold or twist or braid. And from this we get simplex, which is a single fold or a triangle. And it's a synonym for monoplex and also a synonym for uniplex. Now, duplex means twofold, 2 floors in a building, 2 suites in an apartment, two-way communication. And then we have complex, which means manyfold. So multiplex is multi-complex, and it means comprising several interleaved parts. Complexity describes the idea of being unable to see the forest for the trees. Things are interleaved in ways which defy simple or simplex apprehension. However, the result of all the folding and the complication is a new thing in itself. And I hope you can see that there is a relationship between abstraction and complexity. Abstraction seeks to draw away the essence, while complexity seeks to create new things by weaving together old things. Now we need to cover the closely related concepts of encapsulation and information hiding, and these are often used interchangeably with the word abstraction, usually at the cost of clarity. Encapsulation is the process of enclosing one or more things into a single entity. Confusingly, that entity is called an encapsulation. C++ offers a number of encapsulation mechanisms. The class is the most obvious. Take some data and some functions, wrap them up in a pair of braces, and put class, or struct, and an identifier at the front. Of course, there's also the enumeration. Take a bunch of constants, wrap them up in a pair of braces, and put enum and an identifier at the front. Function definitions are a form of encapsulation. Take a bunch of instructions, wrap them up in a pair of braces, and put an identifier in a pair of parentheses, optionally containing parameters, at the front. How about namespaces? Take a bunch of definitions and declarations, wrap them up in a pair of braces, and put namespace and an optional identifier on the outside. Source files work in a similar way. Take a bunch of definitions and declarations, put them in a file, and save it to your file system with a name. Modules are the first new encapsulation mechanism in a long time. These work in a similar way to source files. Take a bunch of definitions and declarations, put them in a file, add the export keyword at the top, and save it to your file system with a name. Encapsulation is only part of the story, as anyone with any experience of modules will tell you. All we have done in each of these examples is gathered things together and named them as a single entity. If we're smart, we will have gathered related things together. Now, information hiding is a more subtle activity, requiring you to make more careful decisions. In addition to gathering, you must decide which items you're going to reveal to the outside world and which you're going to hide. Information hiding implies that some encapsulation is taking place, but encapsulation does not imply that information hiding is taking place. Some of the encapsulation mechanisms of C++ support information hiding. The class offers us access levels. Members within the private implementation are hidden from clients of the struct. This is how we relieve clients of the burden of enforcing class invariants, by hiding the implementation and thus preventing clients from breaking them. The enumeration offers no information hiding. There is no way of exposing only a few members of an enumeration. Functions hide information perfectly by merely exposing an identifier and a return type, while hiding away the implementation. Namespaces can expose declarations and hide definitions by distributing over more than one file. Header and source files do the same thing, as do modules. But abstraction is a tricky word. Matters aren't helped by the fact that the result of abstraction is an abstraction, just as an encapsulation is the result of encapsulation. Let's consider the process of abstraction in the same way that we just considered the process of encapsulation and information hiding. In a programming context, abstraction means identifying and isolating the important parts of a problem, drawing them off, and discarding the remainder. We separate them from the details of implementation we label abstractions with identifiers. Again, consider the nature of functions. We bundle a set of instructions into a single entity and we label it. The function is an abstraction with a name meaningful to the problem domain. Similarly with classes, the class is an abstraction with a name meaningful to the problem domain, containing relevant functionality to model behavior implied by the name. However, the art of abstraction is deciding what should lie within the scope of the abstraction and what should stay outside. And this is where it differs from mere encapsulation. Also, I use the word art advisedly. There is no mechanical method for deciding where to draw the line between what is relevant to the abstraction and what is not. That ability comes with practice and experience. And you'll have heard me use the phrase problem domain. Before I came to this talk, I assumed there was no controversy about the difference between the two. And I was wrong. And simply typing problem domain versus solution domain into Google was quite enlightening. So this is from a blog called Shah World, which has been inactive since July 2017, and it says, problem domain, or problem space, is an engineering term referring to all information that defines the problem and constrains the solution. The constraints being part of the problem. Solution domain defines the abstract environment where the solution is developed. I quite like this definition. He then goes on to say, the differences between those two domains are the cause for possible errors when the solution is planted into the problem domain. And this is a very significant point. Consider the int keyword. Does it live in the problem domain or the solution domain? Now, if you are not on your guard for my asking such questions, you would probably say solution domain. After all, you write C++ programs which solve problems using the built-in type. But what if the problem is, how do you represent data in RAM or in CPU registers? So now, int is part of the problem domain. The solution domain is a pile of assembly language instructions. Problem domains go on to become solution domains for other problems. And we'll look at this again later on. Let's actually look at the CPU and how we got to int. The CPU is what compilers generate code for. This is a diagram of a CPU, which I found on the Red Hat website after a little Googling. I actually found lots and lots of diagrams of CPUs, each with different contents, and I had to find the one that was operating at the correct level of abstraction for this talk. Now you can start anywhere you like really on this diagram. The operation of a CPU is a constant whir of execution and state manipulation. So there's the A and B register, you can see about a third of the way up. They are places where data is stored. And then there's the instruction register, which contains a single instruction. There's actually two here. And here you can see the ALU. The ALU combines registers and instructions to produce a result in the accumulator, which is written back to the L1 data cache. Alternatively, it could be written to the instruction pointer, since the instruction might be a jump, in which case the registers might contain the current instruction pointer and the relative jump size. The L1 data cache may get written back to the next level data caches. The instruction pointer then points to the next instruction to be executed, and then the registers are populated from the data cache, and that may require the cache to be refilled from somewhere else via the memory management unit. This diagram is an abstraction of the silicon that makes up the CPU. The billions of transistors, the substrate manipulation, all of the really mind-bogglingly tricky stuff that process and manufacturers do inside their foundries can be represented by this diagram. The important features are state and execution. State is inspected and manipulated via execution to yield new state. I don't want to sound like I'm overstating this, but the complexity of a CPU is tremendous, increasingly so as the years go by. One thing this diagram lacks is the notion of multiple cores. Branch prediction and instruction look-ahead is unrepresented, and those concepts would complicate the diagram still further and make the abstraction harder to grasp. When we look at the history of programming languages, they all involve state and transformation of state. The first language that I learned was Atom Basic on an Acorn Atom back in 1980. Then I moved on to Sinclair Basic on the ZX81, and then to Z80 assembly language, and then 68,000 assembly language on the Atari ST. All of them involved state and execution at different conceptual distances from the CPU. And when I first started learning C, I was able to apprehend it as a macro assembly language. I could directly map between assembly instructions and C instructions. A for loop looked like a conditional jump back to earlier in the code. A bit shift operation looks exactly like a bit shift operation in 68000. The distance of abstraction was very small. C++, however, offered a different kind of abstraction. Let's take a look. We'll start with the easy stuff. Int is the fundamental built-in type. You may have heard of long or short, but int is the machine word. It can be modified with unsigned, although I advise against this, as well as long and short. And as I said earlier, it is representation of data inside the CPU, be it in registers or the cache. When I first started programming CPUs, the registers were integer registers, particularly on the ZX Spectrum. If you wanted to do any non-integer arithmetic, you had to go to the built-in ROM, which used the RST28 instruction to launch into a fiercely cunning postfix floating point calculator. It was a thing of beauty. In a few kilobytes of Z80 assembly language, it offered a scientific calculator. I still think of it with astonishment. In fact, I spent the whole of the 80s working with integer maths. I worked in millimeters. It seems precise enough for my purposes. I first came across floating point arithmetic in Silicon, with the advent of the Intel 80386. More precisely, there was a maths coprocessor called the 387, and these two devices would work in parallel, and the cunning programmer would be able to work to much greater precision than fixed point arithmetic would allow. You may recall the Intel i486DX. This was the first chip with an integrated maths coprocessor. No longer were two parts needed. Floating point arithmetic was built into the silicon. PCs based on this processor were the gaming rigs of the 1990s. All of this narrative I'm sharing here is contained in the type float. And now, with modern processors, there is a separate set of floating point registers, and the process is considerably simpler. When you use the float type, you are simply selecting one of those registers. Things start to get a little weird with bool. This type is for storing Boolean values, that is, true or false. It would not be unreasonable to assume that this type is represented by a single bit. However, this is not necessarily the case. A quick glance at some output from Compiler Explorer will reveal that it's an 8-bit type for MSVC, GCC and Clang, where 0 means false and everything else means true. This might seem like quite a waste of bits, but the most efficient implementation requires those extra bits. Implementing as a single bit would introduce more complexity to the generated code and would diminish performance. There is a trade-off to be made between size and speed for this abstraction. Now, char is a strange thing. It's a data type with a special purpose, dealing with text. Whereas int and float, and for that matter unsigned int, double and long double, can be seen as analogues of registers or cache data, char has a little extra going on. It's used for storing elements of string literals. When you type a pair of quotation marks and put some text between them, that is the type being used. There is, however, a significant problem. Char is only 8 bits wide in the general case. This width is not specified by C, but the implementers all choose 8 bits for the width of char. Now, as of version 14, Unicode has over 144,000 entries, which means that char is not up to the job for representing the whole gamut of written human expression. Historically, characters 32 to 127 correspond to those in the 7-bit ASCII character set, which forms the basic Latin Unicode character range, and straight away you should detect a problem. The use of the word Latin should alert you to the parochial nature of the choice of letters. But of course, C doesn't care. It was designed for use on Unix, which was a US project. The keyword char is just a hint to the expected use of the type. Unfortunately, as an abstraction for textual representation, it is woefully lacking. The standard has added the type wchar_t for wide characters, which can be 32 or 16 bits wide, depending on your platform. And this is a loss for portability. Such string literals are prefixed with the capital L for wide. Meanwhile, operating system vendors have tried to come up with solutions to improve the representation of text. Windows has API calls for choosing between ANSI and wide characters, which you can switch between by choosing a preprocessor definition before including Windows.h. The Unicode Consortium has catalogued a set of glyphs and provided a library for working with them. C++ has of course inherited this type and added char32_t, char16_t and char8_t for UTF-32, UTF-16 and UTF character representation. It's not a great abstraction for text. There is one more fundamental type, anyone? Yes, void, and I suppose stud null putter_t, which is the type of the null putter literal. So now we have some abstractions for data on the processor. What about abstractions for execution? So this is the plain and simple function. It's easy to tell what it does. It has a meaningful name, which conveys that the parameter is going to be multiplied by itself. Note that the name is clearer than the code, at least marginally. Credibly, you might say that square is potentially ambiguous as a name, while the code is not. Square could mean multiply a number by itself, or form a square of a particular side length, or it could even be a test to see if a number is square. This returns us to the observation that naming is hard. Identifying your abstraction is the most important part of forming one. However, while the C++ code is unambiguous and immediately apprehensible, the assembly code is not. Now, there was a time when C was a high-level programming language and assembly was a low-level programming language, and level here means level of abstraction. Programming in C allows programming at a higher level of abstraction than programming in assembly. Programming in C++ allows programming at a still higher level of abstraction. Nowadays, though, very few people write in x86 assembly language. Consumer chips are so full of bells and whistles to improve performance that it is a waste of time to go straight for assembly, and a better idea to let the compiler optimize your code for you. Of course, forward declaration of functions is another form of hiding complexity. By simply stating that the function exists, you are advertising everything the client needs to know. They do not need to see the implementation. They only need to know that the implementation exists, and that it does what the name of the function seems to imply, or what the accompanying documentation says it does. This is not the only form of abstraction available, though. A new facility in C++, well, new since C, that is function overloading. This allows you to reuse a function name. It's a form of polymorphism. The name is the important thing. The implementation is unimportant. Another way of viewing this is that the abstraction is independent of the type. It doesn't matter whether you're trying to square an integer or a floating point type. Square means the same thing. What complexity does this hide? Simply the type of the object being operated upon. We're left with the pure name, and we can go still further. This is a generic function, making explicit that the algorithm is irrelevant to the type, hiding yet more complexity. The use of requires clauses can further refine the declaration to make clear what kinds of type can be passed in. And then, of course, we have lambda expressions, which construct a closure, an unnamed function object capable of capturing variables in scope. These are functions that can be passed around to functions. Again, hiding complexity, this time the complexity of mucking around with function pointers. I said just now that programming in C++ allows programming at a still higher level of abstraction. Consider what it means to program at a higher level of abstraction, though. The native assembly instructions are replaced with more understandable C instructions. The complexity of assembly language is replaced with the relative simplicity of C instructions. But what about C++? Is that an even higher level language? Well, consider this example of a house. It's a struct, which you can think of as a record in a database table. And in C, a typical interface might look like this. But this seems like a rather verbose way of modifying the members of the struct, given that you have a pointer to fit it into it in the first place. I detest trivial getters and setters, and that is precisely what you can see here. Now, you could always write superior non-trivial interfaces, but it's all too easy to turn this into an untidy API, and you are still exposing the data to client interference. Classes make things a lot easier, especially with some of the additional features of C++. In a break with tradition, I have put the private interface at the top so you can more easily observe what's going on. One thing that C functions allow you to do is to abstract problem domain activity into the solution domain, and I'm foreshadowing here how model view controller methodology can improve the level of abstraction, which we'll look at later. Class polymorphism is not new to C++. It was available in C, although you had to hand-roll your solution, and it would look something like this. You could write code by switching on the has type and calling the appropriate function, like so. And all sorts of weird things could go wrong here. You would have to manually ensure that you covered all cases. You would have to ensure that if a new enumeration was added to has type, all places where the enumeration was used would consider it. This is a terrifically hard problem, requiring extremely disciplined behaviour on the part of your engineers. However, this was widespread practice, switching behaviour on a type field in a struct. Now we have the virtual keyword. So I've restored the public interface to the top of the class declaration. The virtual keyword signals to the client that the function dispatch may be resolved at runtime. There are a mix of pure virtual functions and regular virtual functions in the interface. Add a flaw provides default behaviour for when doing so isn't meaningful. What complexity does this hide? It hides the complexity of choosing behaviour based on dynamic type. By overriding virtual functions in a subclass, the switch case statement is rendered completely unnecessary. This complexity is not necessarily part of the CPU. It is part of the way that programmers write code. And I'm going to have to point out here, of course, that virtual functions do carry quite a penalty. The code needs to inspect the virtual function table, locate the function pointer, and then call the function. And this means a data cache miss and an instruction cache miss. Caches are quite modern inventions in the grand scheme of things. The virtual keyword enabling automatic dynamic dispatch was introduced in the 80s, while caches were introduced a good 15 years later. This doesn't mean that you should stop using virtual functions. It means that you should weigh up the cost when you decide how to approach the problem. If you go back to rolling your own switch case-based solution, you will suffer the same penalties. The question you should be asking is, how did you manage to lose the static type of your object? Solve that problem, and you won't need to resolve function dispatch dynamically. For example, when you create an object of unknown static type, store it at creation in a collection with other objects of the same type. Losing sight of the static type of an object is a costly design decision to make. Static polymorphism is also available to classes, just as it is with functions. This takes a little more consideration. Recall that polymorphism eliminates implementation detail. It retains the identifier without having to specify certain parts of the abstraction, particularly the types. Dynamic polymorphism hides all the type information in a virtual function pointer table. Static polymorphism hides all the type information behind template parameters. And this is the most obvious with the standard library containers. What complexity is this abstraction hiding? It is the complexity of implementing the data structure for a particular type. A class is a set of functions and data with some invariants. If the data types don't matter, they can become template parameters. In fact, recall the full definition of a vector. The mechanism of defaulting is another abstraction mechanism. What complexity is it hiding? It is hiding the complexity of default behavior. This is not a trivial problem, and it's solved for you by default arguments. There are other abstraction facilities offered by the class and struct furniture, but you get the idea. The class is the primary piece of problem domain abstraction. It enables you to model things from the problem domain in the solution domain. A meaningful name and a credible API are the essence of your abstraction. But to reiterate, structs and classes abstract from the problem domain. Functions and built-in types abstract from the solution domain. Problem domains become solution domains, and this last point is very important, and we'll see an example of it later when we look at the OSI model. Here's an interesting question. Are namespaces an abstraction facility? After all, they take a bunch of declarations, wrap them up in a pair of curly braces, and give them a name. The effect of declaring something in a namespace means it goes from this to this. Is this hiding any complexity? I don't think it is. Namespaces provide a facility to disambiguate common names, which does not remove complexity. It makes the code easier to read, it increases the number of useful names you can give to declarations, but it isn't hiding any complexity. If anything, it is preventing complexity. For example, look at these two function names. It is quite usual to name abstractions by domain and then by abstraction, so that you know whereabouts the things live and what they're for. And this is fine while your code base is reasonably small, but once you reach 1 million lines of code, which is not at all uncommon in game development, you're in danger of naming things like this. And this becomes pointless if you're writing code inside the AI entity code. Nothing is served by making your names long and prefixing them with AI_entity. The facility of namespaces allows you to offer domains of abstraction to the compiler and a simpler means of disambiguation. It does bring its own problems though. This is a using directive. The core guidelines suggest you should avoid declaring a using directive in a header file. There is an exception actually, which is the std literals namespace. You need this to use string literals in header files. However, I don't think the core guideline goes far enough. I think, with the exception of the std literals namespace, you should never use a using directive. And I devote a whole chapter of the book to why you shouldn't do this. But briefly, a using directive does not only introduce new symbols into the current scope. A using directive introduces its new meanings into the scope, which is the lowest common ancestor of the current scope and the target namespace's own scope. And this can be quite surprising and becomes more surprising as a code base grows and acquires more namespaces. We're drifting off topic a little bit here. I won't go into detail, but it suffices to say, I advise against using directives, nor is a namespace an abstraction facility, despite appearances. Libraries, on the other hand, are most definitely an abstraction facility. In tandem with header files, they have the bread and butter of code reuse ever since C was a twinkle in Kernighan and Ritchie's eyes. It's a simple mechanism. What's going on here is that the compiler parses the declarations in mystuff.h and uses that to inform the remainder of the translation unit. And this is great. You have a consistent way of making a set of declarations and reusing them in other translation units. You are able to adhere to the one definition rule and have that one definition be consistent. Brilliant. The definitions of those declarations are either made in the header file with static linkage or included in a library file. There we are. mystuff.lib abstracts all the implementation complexity behind a simple header file. And we've been using this mechanism for a long time now. It's not without its costs though, and this leads us to the question of what is a zero-cost abstraction? And I'll answer that after we cover modules, which are the first new language level abstraction for, it's the first new language level abstraction facility for a long time. Now consider the inclusion model. The problem it solves is ensuring identical redeclaration of types and functions by means of lexical substitution. When you type #include matrix.h, the preprocessor will hunt around for that file, open it, and add it to the stream of text for compilation. It comes with a few problems though. The mechanism used by the preprocessor to find the file is implementation defined. What works on one toolset may not work on another. The preprocessor is language agnostic, so it knows nothing about whether or not the code is correct during inclusion, potentially burning up valuable time before the compiler gets to it and tells you that it's malformed. It relies on the linker to provide the definitions for these declarations, which again knows nothing about compilation. The inclusion model attempts to solve the problem of code reuse without using the compiler at all, and this means that opportunities for optimization are lost. We can and we must do better, so enter modules. The big deal with modules is that they turn libraries and programs into reusable components. A module is a set of source code files that are compiled independently of the translation units that import them. They have no effect on the compilation of the translation unit that imports the module. After a module is compiled once, the results are stored in a binary file that describes all the exported types, functions, function templates, and class templates. The compiler can process that file much faster than a header file, and the compiler can reuse it every place where the module is imported in a project. Proposing modules came with a big pile of problems to solve. What do you do about preprocessor symbols? Argument-dependent lookup. It took a long time to answer those questions. And this isn't a primer on modules, so I won't go into the results, but I will give you a quick example of what a module looks like. And this is shamelessly lifted from the modules page on CppReference.com. And incidentally, that page says in its own paragraph that modules are orthogonal to namespaces. And this is worth mulling over. From the top, the first line informs us that we are declaring a module. And the second line imports IO stream. And note that it doesn't include it, it imports it. When the compiler imports IOStream, it will see that it is not a module since it doesn't contain an export keyword. The third line actually defines something, a function called hello, and marks it for export into the module defined by this source file. So let's look at a source file which consumes this module. So I hope this is reasonably obvious. At line 1, rather than include hello world, we import hello world. Otherwise things don't look too different from the familiar include model. The source file main.cpp is importing a definition, a void function called hello, and calling it. Now, I'm not an implementer, those folk are amazing and I just write games. However, I would like to think that my mental model of the inclusion process is not too far from the import process. I imagine that when I hit build in my IDE, the dependency scanner will look at the modules and build them first if necessary, and then simply add them to the compilation stream as requested by the import declaration. If you're familiar with precompiled headers, you may see parallels here, but modules are not precompiled headers. Modules can selectively export names, while precompiled headers export everything. Now, looking back at the import of IOStream, when hello world.cpp is compiled and turned not into an object file but a module, it will include all the types, functions and templates that are declared in that file. It only needs to be parsed and built once rather than every time, as is the case with headers. This alone justifies the use of modules for me. What complexity is this hiding? Well, it's the obvious question, particularly though, where we were using the preprocessor and the linker to enable the reusing of code, with all the problems that brings, we are now doing it within the compiler itself, with much finer grained control available. We've migrated from encapsulation to abstraction by offering the encapsulation in place and offering control in the solution domain. You might think that this means the end of the linker, or at the very least the librarian, but there are some considerations. For example, with Microsoft's compiler, a module and the code that consumes it must be compiled with the same compiler options. And also, if you want to consume the C++ standard library as modules, you must compile your program with /ehsc and /md. That is standard stack unwinding in the DLL version of the standard library. Stack unwinding is an expensive feature to add to your program, and not one that I'm inclined to use in game development. Just one moment, please. Now, I imagine you're all aware of this picture, and you may even be able to explain it in detail. I want to present the Open Systems Interconnect model in terms of levels of abstraction. So level 1 is the physical layer. The physical layer is responsible for the transmission and reception of unstructured raw data between a device, such as a network interface controller, Ethernet hub, network switch, and a transmission medium, such as optical fiber or copper cable or even an antenna in the atmosphere for Wi-Fi transmission. It converts the digital bits into optical, electrical or radio signals. The specifications of the physical layer include things like voltage levels or voltage change timings and physical data rates and so on. It's stuff to do with the wiggling about of electrons. This is soldering iron stuff, the arena of the electronics engineer. These specifications are the abstraction. However the physical layer is implemented, either as a simple Ethernet card or as a network switch, there is a consistent interface to the hardware, and this interface is exploited by layer 2, the data link layer. Layer 2 doesn't care how layer 1 is implemented. It simply relies on the specifications being adhered to. It takes advantage of the abstraction offered by layer 1 to carry out its task, which is the transfer of data between nodes. It handles establishing and terminating a connection, error detection and correction, and flow control between the two nodes. It requires no knowledge at all of whether or not the data is transferred by light pulse or electrical voltage deltas. If you're into standardization, you will know that IEEE 802 operates at this layer, featuring specifications such as 802.3 Ethernet and 802.11 Wi-Fi. These operate at the data link layer. This layer is what you are interested in when you subscribe to broadband. The point-to-point protocol is a data link layer protocol that can operate over several different physical layers because those level 1 physical layers all expose their operation in the same way. Next up is the network layer, layer 3. It transfers packets. Now, it's really easy to describe, but there's a lot going on under the hood. For example, it handles routing packets to the correct destination or splitting packets that are too large. Interestingly, there is no guarantee of reliability, nor of error reporting. so I'm hoping you can see a picture emerging of dependency upon abstraction. Looking at layer 4, the transport layer provides the functional and procedural means of transferring variable length data sequences from a source host to a destination host, from one application to another across a network, while maintaining the quality of service functions. This may require breaking large protocol data units or long data streams into smaller segments, since the network layer imposes a maximum packet size called the maximum transmission unit (MTU), which depends on the maximum packet size imposed by all data link layers on the network path between the two hosts. The transport layer also controls the reliability of a given link between a source and destination host through flow control, error control, and acknowledgements of sequence and existence. Reliability, however, is not a strict requirement within the transport layer. Protocols like UDP, for example, are used in applications that are willing to accept some packet loss, or reordering, or errors, or duplication, streaming media, real-time multiplayer games, and voice over IP are examples of applications in which loss of packets is not usually a fatal problem. Layer 5 is the session layer. The session layer creates the setup, controls the connections, and ends the teardown between two or more computers, which is called a session. Since DNS operates in this part of the layer, common functions of the session layer include user logon and name lookup and user logoff functions, and this might start to sound like C++ programming. You could implement all of this using constructors and destructors, because sessions have a well-defined start and end point. The session layer establishes, manages, and terminates the connections between the local and remote application. All of this relies on the prior layer, the transport layer, being able to move data from device to device. I hope this is becoming clear. Complexity is being hidden by well-defined layers of operation. This is layered abstraction. So layer 6 is the presentation layer. It establishes data formatting and data translation, protocol conversion, encryption, compression, and so on, and it relies on the session layer to have correctly established the communication points and the context that brings with it. And layer 7 is the application layer, which defines the protocols to use, which compression, which encryption. HTTP and SMTP are application layer protocols. You're all programmers, and I imagine you're pretty familiar with protocols like this. Let's look at a more concrete example of file parser for command line options. Now, imagine early in the execution of my program, I want to read in some options from an external file identified on the command line. The options are declared as key value pairs, and there are only a dozen possible options, but being a smart engineer, I decided to create a separate function for doing this, and I'm going to call it parse options file. And it will take a file name, which I will pull out of the command line, and if none is declared, I will not call the function. So let's take a moment to review what's going on here. The function body is simple. Open the file, read each option line by line, and update the state appropriately until we reach the end of the file. I can easily add new options in one place and withdraw old options without any hassle. If the file contains invalid options, I can just notify the user in the final else declaration. Now, a couple of days later, a new option is defined, whose value could be several words. And that's fine, I think. I can just read until the end of the line in that option, and I'll create a 500 character buffer and make a string from it. Now, I've come up with a simple, flexible way of parsing options. I can just add code for each option. Now, the following week, a colleague tells me that some of the tokens are only valid if the user has set the debug flag. Well, that's also fine. I set the debug flag at the top of the function so I can query it later in the function and be sure that I only apply tokens when they're applicable. Mind you, I'm keeping track of state now, and that is something to be mindful of. The next month, incorrect preferences files are causing a stir, and I'm asked to apply the preferences only if they are all valid. I sigh, that's fine, I can create a preferences object containing all the new state and return that if it is valid. Stood optional will come in useful here. Unfortunately, this function is so useful that other people have started using the options file. There are now 115 preferences being parsed, and I appear to have created an enormous junction box with lots of state and a bajillion conditional statements. Every bug related to the preferences file is going to be mine to solve, regardless of who put it there. That's just how people work. How can we fix things? Well, you might decide to declare a single function for each option. This is a good idea because it at least highlights that the responsibility for bad behaviour lies with the person who wrote the individual option's parsing function. It will be hard for people to wriggle out of that responsibility and land it on me. Validity can be checked and reported within each function. You can signal an error somewhere somehow, or send a note to standard output. We've encapsulated all the different options in their own function, and we can easily add further functions for new options, growing the parsing function for each one. Still need a way of tracking the validity of the options file. Other users of the function should get the hang of things now. They will see the pattern and they'll follow it. Or will they? Because my spidey senses would be kicking off about now. There are so many places where this could go wrong. So let's bring abstraction to the party. We are trying to parse a file of key value pairs and apply the results to the environment if they're valid. The function is well named, parse options file. The problem we have is safely adding arbitrary key value pairs. Is the identity of the full set of pairs actually relevant to parse options file? Is it within scope? Can we separate the options from the function? At the moment, we're simply pulling keys from the file and checking each in an ever-growing if-else statement, since we cannot switch case on strings. This sounds like an associative container. In fact, a map of keys against function pointers sounds perfect here. Suddenly, our function has lost a huge amount of repetition and been replaced with a single interrogation of a map and a corresponding function call. The important part of this function is that it parses an options file and does something with each key. Unfortunately, along the way, we have lost the capability for values to contain spaces. The chevron operator will stop extracting when it reaches white space. However, this is certainly feeling better. All we must do is initialize the map of keys and function pointers. Unfortunately, we've just moved the problem around. The initializer is another point where users can trip up. It's easy to forget to update the initializer. Perhaps we can automate that. Well, yeah, actually, we absolutely can. Rather than mapping keys against function pointers, we can map them against function objects with constructors and create static objects rather than functions. The constructor can insert the address of the object into the map. In fact, we can derive all the function objects from a base class that will do that for us. And also, now that we have a base class, we can add a validation function and perform a validation pass, followed by a commit pass. It all seems to be coming together. Indeed, you might think that we're all done here. Abstraction has carefully separated the options from the parsing function. Parse options file is like the session layer and the presentation layer in the OSI model, while the individual classes are like the application layer. But if parse options file is like the session layer and the presentation layer, does that imply that more abstraction is available? Absolutely. Because although we are parsing an options file, we are only actually reading a series of characters. They do not have to come from a file. They could come from the command line itself. We should rename the function parse options and change the input parameter to a std stream. So look at this beauty. We are taking a stream, pulling out the key and value, and then invoking the matching option function. And as a bonus, if we don't find an option, we could decide it's a file name and then open up the file and continue parsing. We get batch files for free. In fact, why are we pulling out the value? Because if we tell the commands to take a stream rather than a value, then the command can worry about extracting multiple values as appropriate. In fact, better still, now that we have separate function objects for each key, we're not limited to initializing data. We can treat each key as a command, and suddenly we have a basic scripting facility. Whereas at the start of this example, the engineer had to extend a function in an unbounded fashion, all they must do now is derive a new class from command and override and validate and commit. We've now moved from a single, potentially enormous parsing function to a small, bounded function and a dictionary of parsing objects. We've also gained command line parsing at very little cost as an added extra. This was all achieved by considering what was relevant to which part of the problem. What started life as a messy construct has become a clean and easily maintainable scripting facility with bonus content. Everybody wins. There's a larger point at work here. Do you know why I like writing games? Nobody dies. If I release a game with a bug in the code, the worst that happens is the game will misbehave or crash and users will get grumpy and they will flame the notice boards, or if they're sensible and have a sense of proportion, they will simply restart the game. It's not medical imaging equipment. It's not a tidal barrier controller. It's not a nuclear reactor. This is a picture of a nuclear reactor. Actually, it's not a nuclear reactor. It's the control room for a nuclear reactor. Particularly, it's the control room for Chernobyl, Unit 3. When it comes to complexity, a nuclear reactor is hard to beat. I really do not know how to operate a nuclear reactor. There are many kinds of reactor, but until we can solve fusion, they all work on the principle of nuclear fission, releasing vast amounts of energy per atom. The control room is staffed by several technicians with different sets of expertise who monitor a particular part of the system. Those technicians gather information, make decisions, and then respond to that information. They're rather like state machines in that regard. They gather information from all of the feedback devices scattered about the control room. Some of these devices are little needles that rotate from right to left as something decreases, like the volume of fuel. They may be numeric displays or 270-degree displays. There are all sorts of ways of presenting information, but the point is that they are all presenting information. I remember when I was a child, I used to look at my grandfather's barometer, and it had two needles, rather like this one. The dark needle would show the air pressure, and the brass needle would be used to record the air pressure at a moment in time. And every morning, as my grandfather went to work, he would tap the barometer and say, down by 12, going to be windy, or whatever was appropriate, and move the brass needle. And one day I asked him, could you control the air pressure with the needle? He laughed and said he wished it were so, because then he wouldn't have to go to work ever again. Back in our nuclear reactor control room, if the technicians wanted to reduce the output of the nuclear reactor, they would turn the knob on the left anti-clockwise. Now, this is me just having a joke. This is an air conditioning control unit. The display, though, doesn't change at all. All that changes is the position of the knob under human activity and the operation of the air conditioning unit. This is a description of human activity that scales well. It's how we interface with machines. We collect input, decide on changes, and enact those changes, be it an air conditioning system controlled by someone in a warm room, or a nuclear reactor controlled by 10 technicians, or a healthcare system controlled by thousands. The process is collect information, decide, enact. I know I appear to be labouring the point, but bear with me, because we're now going to talk about my most hated API decision. Let's talk about this piece of code. This is an example of using trivial getters and setters. They simply reach into the implementation of the class and return or modify the value. On the surface, there are some things to commend in this approach. You can search your codebase for get_x and set_x to see where the code changes x. Alternatively, it's easy to set a breakpoint in the function so that you can track every instance of where the value is retrieved or modified. It honours the idea of keeping data private. The data is encapsulated behind an API. There is a core guideline, C.131, avoid trivial getters and setters, advising against this approach. They are trivial functions which simply put a roadblock in the way of direct access to X. Now look at this barrier. Is it at all effective? It is not, unless you are trying to prevent people who don't like driving on the grass from getting past. And this is a great metaphor for get-set functions. I want to take you back to the days of C. Now, without access specification, all data is available to everything. Significantly, it was usual for data that was not in the scope of the currently executing function to be directly available for modification. Typically, you would see something like this. Now, if the engineer was lucky enough to be the only person expected to modify such data, they would be able to reason about it with a valuable degree of certainty. They knew where the data was modified, and they knew where the data was read, and they would therefore be able to identify bugs related to the data. But sadly, as teams grew bigger and individual pieces of data became more important, keeping hold of responsibility for them became harder. The data would be declared in a header file, making it accessible to many engineers. Reasoning about the data would become a lost cause. Coding guidelines would be written about the data. Arguments would break out in the kitchen about who was mucking about with it. Meetings would be called to set policy once and for all about who was allowed to write to the data and under what conditions. Documentation would be added to the declaration, and everyone would hope that it was being kept up to date by someone who wasn't them. Everyone would hope that all the other engineers were reasoning about the data in the same way. Everyone would hope 6 months later that all the other engineers were continuing to reason about the data in the same way. Now, the important thing to remember is that once data is declared in a header file as an extern declaration, not only is all control lost, but all hope of control is also lost. And whatever you think you might mean by this piece of data, Hiram's law applies. With a sufficient number of users of an API, it does not matter what you promise in the contract. All observable behaviors of your system will be depended on by somebody. You no longer own the data, and yet you remain responsible for it. Searching the codebase for an identifier with a useful and therefore common name becomes a nightmare of context assessment. Eventually, a bright engineer would hide away the piece of data behind a pair of functions, one to write the data and one to read from the data. And it would not make reasoning about the data any easier, but a search through the codebase for the call sites of those functions, along with a breakpoint of those functions, would combine to reveal under what circumstances the data was being changed. And if they were really clever, they would find a way of naming the functions to reflect what their purpose was in the problem domain, in an attempt at producing self-documenting code. For example, if the piece of data was an elevation above sea level, they might name the functions like this. Now, this would not prevent people from arbitrarily changing heights at inopportune moments throughout the codebase, but at least it would signal what they were doing, and perhaps improve client readability by using nouns for functions that queried values and verbs for functions that modified values. Gatekeeping the data in this way allows you to search for its uses, and you get the added bonus of being able to set breakpoints in your debuggers so that you can keep a careful watch over it. And then along came C with classes, with access levels and member functions. Access levels! Finally, the data belongs to me. I can make it mine by declaring it private. Then nobody can touch it, except through one of the public member functions. Member functions! In C, it was possible to store pointers to arbitrary functions in structs, but member functions, with an implicit instance pointer as the first function parameter, were a leap in usability. The world was a brighter, shinier place. The programming style of hiding your data behind a pair of functions was no longer simply a bright idea, it became normal practice, enforceable by the language itself. New advice was offered, loud and clear: make all your data members private. A new keyword was added, class, to distinguish from struct. For backward compatibility, members of structs remained public by default, while members of classes were private by default, reinforcing the idea that data should be private. With the ability to keep data in a private interface came the opportunity to prevent, trivially, people from interfering with that data. You could create an object and provide getSet functions to get at the data. And this, in a nutshell, is encapsulation. Encapsulation is one of the core principles of object-oriented programming, restricting access to the object's parts, to combining data with the functions that operate on that data. And it's a safety feature that easily improves the ability of the engineer and the users of the encapsulation to reason about what is going on. Suddenly, encapsulation was available to C engineers, and this sort of thing happened. Yeah, remember this. This saddens me enormously. What is the actual difference between this and a struct of the public data, semantically? While it is true to say that this is an API, it's also true to say that the plain struct made more sense semantically. The API could be described as a set of functions to read and manipulate the house data. We're trying to hide complexity away here with classes, and this is precisely the opposite of that. The trouble is, coding standards emerged with edicts like all data should be private and should have a get and set method. There may even be an instance that get functions should be const qualified. The sunlit uplands of bug-free code were just over the next hill. The drinks were on the house, but hang on, what have we actually gained here? This sounds no different from the problems we used to have. We're still stuck with having to worry about the data being modified by other people. What is the point of the functions to get at the data? Adding get and set functions doesn't make this interface safer or less error-prone. It's just another way in for bugs. The question you need to ask is why you care about people modifying the data. Does arbitrary tweaking of member data invalidate instances of your class? Is there some restriction on your data? If so, then your setter function needs to do a little work. For example, the floor area should not exceed the area of the plot. Now, this setter function is no longer trivial, and it has a reason to exist. The condition that the floor area cannot exceed the size of the plot is known as a class invariant. More generally, a class invariant is a condition that must hold for all valid instances of a class. Access levels allow a class designer to easily preserve class invariants by checking the effect of operations on the member data and ensuring that all the data retains valid values. This guideline gives us its reason. A trivial getter or setter adds no semantic value. The data item could just as well be public. And as we can see from the has example, that is exactly the case. There is no semantic difference between struct house and class house. The member functions are redundant. There is an operational difference in that there is an opportunity to set breakpoints where the member data is read and written, but that has no impact on the semantic nature of the house abstraction. When creating a class and designing its interface, it's quite usual to think of aspects of the abstraction being modelled with numbers. This is a computer you're writing for, after all. The temptation becomes simply to make those aspects numerical data members. And if a client wants to change something, they call the function to set the new value, and after some checking to maintain class invariance, the corresponding data member is modified appropriately. A class is not an empty vessel for pouring data into. It is to be used as an abstraction of the problem domain into the solution domain. If there is one thing I want you to take away from this talk, that is it. But this is rather missing the point of good class design. A class is an abstraction of an idea, not a bundle of data. The reason why change height and height are good function identifiers is because they convey, in English, what's going on. The client engineer doesn't care that they are changing an int by some amount. They care that they are changing the height of the object. They don't want to know the value of the height member. They want to know the height of the object. These two things operate at different levels of abstraction, and leaking abstraction details is bad practice, unnecessarily increasing the cognitive load of the client engineer. Go back to the introduction. My suggestion was that everything works by collecting information, making a decision, and then acting on that decision. In this piece of source, you can see that the client engineer is going to call the height function, make a decision, and then call the change height function. Now we know what these parts of speech are, and we should use this information to improve the quality of our conversation with our engineer. This is the important part. Change height is a verb. Height is a noun. And when you look at it in those terms, suddenly the ideal API becomes a lot more apparent. Do you think this is any better? How about this? We can see that there are two things you want to do with an elevation. You want to change it or set it. But Guy, I hear you say, over the ether, that's a setter function. And yes, it is, but only because I cannot think of a better name than set elevation. The semantic is not diminished, the elevation just happens to be implemented in terms of a number, so it looks like I'm directly writing to the data. Actually, my inability to think of a better name makes me wonder if I have the right abstraction here anyway. Am I losing clarity by having to use a name as generic as set or change? Is there a better abstraction, something which hides complexity, waiting to be found, that explains things in clearer English? The trick here is to think in terms of nouns and verbs. Code becomes more legible if you have single words describing what you're doing to what things. Underscores make reading harder. So fun fact, the first parameter of a member function is implicitly this. So this function here, report, is implemented thus. Of course, you never see the initial parameter because it's unnecessary. What is less widely known is that you can overload functions by reference qualification. So here's an example, which are implemented like this. The compilable sect selects the overload based on whether or not the object is an R value. So for example, like this. And this is really quite useful. The function knows that this is the very last function that will be executed before destruction. That means that any data member can be safely moved out of the object rather than copied, which is always to be preferred. Copying can be expensive. That leads to multiple instances of the same object, which makes reasoning harder. Note that if you ref qualify one function, you have to ref qualify all the overloads. So you're probably more familiar with this third overload. And I really hope you have never seen nor are ever attempted to use this fourth overload. You have some awful problems ahead of you if you see this. We'll just get rid of that overload. So this new overload is implemented like this. And incidentally, this is why I prefer East Const. Bundling all the qualifications together improves clarity for me and has greater semantic strength and conviction. This third overload deduces this to be const, and so forbids the mutation of any member data. There's a chance that this still looks weird to you. The rule is that if you specify the ref qualification for one overload, you have to specify for all of them. And if we discard the R-value ref qualified overload, we can get rid of all the ampersands. Let's look at some examples. So as you can see, we're trying to modify member data in the function which deduces this to be const, so we get a compilation error. A const qualified member function can only inspect the member data, not mutate it. So let's go back to our gauges and knobs metaphor. This function is a gauge, not a knob. It simply tells you things. It doesn't change things. It's a view function. And this seems to imply that repeated calls to a const member function are guaranteed to return the same result until a non-const member function is called. However, this is not necessarily the case. Look at this. So imagine that the magic number is calculated according to the current state of the object, that the calculation is super expensive, and that the object doesn't change very often. You might decide you want to cache the value. And as you can see, we've added 2 new members to cache the value and mark if the cache is dirty. Unfortunately, we can't update them in a const qualified member function. What to do? Well, we have this keyword, mutable, which signals that the member data is immune to const qualification. This also has use for thread safety. If you make your mutexes mutable, you'll be able to lock objects while they're being inspected. So we should probably also consider the notion of overloading on ref qualification and const qualification. What would that mean? The implication is that the word report is performing double duty, and if you have a function identifier that makes sense as both a noun and a verb, then you've probably chosen an unwise name. So I have a piece of advice therefore. Naming is hard, but misnaming is harder to live with. So don't do that. When you give a function a name, you are attempting to precisely capture the operation of the function in a single noun or verb. Nouns are properties of the abstraction, while verbs are mutations of the abstraction. And this makes much more sense. We definitely have a verb being used to change things, and that verb, create report, also highlights that the noun, report, is indeed a noun and not to be interpreted as a verb. The const qualifier also reinforces that notion, but the first thing you see is the function name. Now, what do we really mean by modelling? Who knows what this is? This is a Lego model of a great jazz album, Survivor's Suite, by Keith Jarrett, recorded in April 1976. This is the original cover. Now, here they are side by side. And what's the difference between the two? There are things like photo quality, lighting, the absence of text, the placement of the chairs, the shape of the pool out of the pitch of the roof. But when I first saw the Lego model, I immediately thought of the original album cover, no hesitation. The important thing with modelling is that you are constructing an approximation of the original, using the relevant parts salient to the problem at hand. When we create a class to abstract something like a house, the chances are that the relevant parts are as described earlier. How much land, how much floor space, how many stories, how many rooms and windows. And this is fine if you're an urban planner. But what if you're an architect? Important information includes the volume of materials required, the nature of the materials themselves, what the walls and roof are made of, how deep the foundations go. The point about modelling is that it's a relevant approximation, in less detail than the original, captured in terms of numbers. Recall class invariants from the getters and setters section. Those invariants constrain the values of the parts of the model. For example, a door to the house may only open up to 90 degrees. The ground floor window shutters may open up to 180 degrees. There may be a door or window class, instances of which may contribute to the house class. Describing these constraints and checking the invariants under modification. If there are class invariants, then the model needs to be private. And this implies a public interface to control and view the model. And this is the essence of model view controller paradigm. Let's look at an API. I hope you can see that the class is neatly divided into 3 parts. The model interface, the view interface, and the controller interface, along with what I call the life cycle interface of construction, destruction, and assignment. I use this approach to my classes wherever possible. It speaks to the clients, telling them how to use the object. You can use this approach to describe the nuclear reactor control room. The reactor core is the model, the gauges are the view, and the knobs are the control. And there we have it. We looked at the nature of abstraction, the etymology, the confusion with data hiding and encapsulation, and we clarified problem domain against solution domain. Then we examined the way that C++ supports abstraction. Next, we looked at some examples of how abstraction is put into practice in the hope of divining how to cement the idea of working at the correct level of abstraction. And then we looked at some bad API design, getters and setters, and the abuse of classes. And finally, we looked at API design as the hiding of complexity through model view controller programming and the correct use of classes. Bonus content. So, as an aside, I want to talk to you about classes versus namespaces. What happens when there is only one of an abstraction and it endures for the duration of the program? You declare it a file scope, preferably within a namespace, and you define it in a source file. And then anyone can retrieve the abstraction, do what they need, and all is good. Except it's not. You've created a global object. Globals are bad, okay? Global objects have no access restrictions. If you can see it, you can interact with it. Global objects have no owner other than the program itself, which means no single entity is responsible for it. Global objects have static storage duration, so they're initialized at startup and destroyed at shutdown. This is problematic. Ownership is fundamental to reasoning about objects. Since nothing owns a global object, how can you reason about its state at any time? You might be calling functions on that object, and then suddenly, and without warning, another entity may call other functions on that object without your knowledge. Worse still, since nothing owns global objects, their construction sequence is not determined by the standard. You have no idea in which order global objects will be constructed, which leads to the static initialization order fiasco. Now, those of you with long memories or good taste will have read the design patterns book. One of the patterns was known as the Singleton pattern. A popular example of a singleton is the main window. The main window is where all the action happens, collecting user input and displaying results, and you should only create one main window, so it might make sense to prevent the creation of another. Another example is the manager class. This is characterized by including the name manager in the identifier, and this is a strong sign that in fact a singleton has been created and that there are problems deciding about ownership of whatever is being managed. The core guidelines include entry I.3, avoid singletons. And the reason is that singletons are basically complicated global objects in disguise. Enforcing this is particularly hard. The guideline advises three things. Look for classes with names that include singleton. This might seem somewhat specious, but since singleton is one of the design patterns, it's remarkably common for engineers to add it to the name of a class to identify that this is a singleton, or I have read the design patterns book. Of course, doing so embeds the implementation in the interface, which is a bad thing. That's another topic. The second idea offered by the guideline is look for classes for which only a single object is created, by counting objects or by examining constructors. This requires a complete manual class-by-class audit of your codebase. Sometimes singletons are created by accident. An abstraction may be inducted and a class formed from it, and all the scaffolding required to manage the lifecycle of and interactions with that class may be created, such as the special functions, public interface, and so on. But only one instance of the object may ever exist at one time. It may not have been the engineer's intention to create a singleton. But that is what has happened. A count of all the instances reveals the quantity to be 1. The final idea is, if a class X has a public static function that contains a function local static of the class type X and returns a pointer or a reference to it, ban that. So the class may have a superset of the following interface. The giveaway here is the private constructor. Nothing can create this object except a static member or a friend, and we see no friend declarations. Nothing can derive from it unless another constructor is added to the non-private interface. The private constructor indicates that my construction is tightly controlled by other functions in my interface. And lo and behold, the public interface contains a static function which returns a reference to an instance. Now, throughout the teaching of C++, there have been some popular examples to describe object orientation. Gas stations have cars, pumps, a cash desk, tankers delivering fuel, prices, and so on, yielding an ecosystem rich enough to describe many kinds of relationships. In the same vein, restaurants have tables, customers, menus, a serving hatch, wait staff, chefs, food deliveries, garbage collection, and other features. In today's textbooks, they probably also have a website and a Twitter account. Both examples have one thing in common. An abstraction that should only exist singly. The gas station has one cash desk. The restaurant has one serving hatch. Surely these are singletons. If not, what is to be done? Well, look at this. It's a class with private data, but the member functions are all static because there is only one of them. And there are two things wrong here. The first is never ever use float for currency. Please count in pennies, or the smallest division of your currency. There, that's better. The second thing that's wrong is the private static data. Only one of them each exist. Why attach it to a class? Why not simply define it in the source file where the member functions are defined? In fact, why are you bothering with a class at all? You can't mark static functions as const because there is no this attached to the function. What is the difference between this and this? What we have arrived at is the correct solution to the problem of singletons. They should be implemented as namespaces rather than classes. The implementation does not need to be exposed to the client like some Heath Robinson drawing of marvellous and fascinating complexity. It can be hidden away in the dark recesses of a private implementation file. This has the additional advantage of improving the stability of the file in which the namespace is declared, minimizing large-scale dependent recompilation. Of course, the data used to model the abstraction will not be owned by an object, so it will be static. Beware of the static initialization order fiasco as described above. You might be looking at this namespace solution and remarking to yourself, but this is still a singleton. It's not a singleton, it's a singleton. The problem that the guideline is warning about is the singleton pattern, not the existence of single instance abstractions. Indeed, in an interview with Informit in 2009, Eric Gamma, one of the 4 authors of Design Patterns, remarked that he wanted to remove singleton from the catalogue. And earlier, we remarked that you may be thinking that all static objects are singletons, so all static objects should be avoided. You should be able to see now that static objects are not singletons, nor are they necessarily singletons. They are an instance of an object whose duration is the entire duration of the program. They are not necessarily globals. Static data members have class scope, not global scope. Similarly, globals are bad and K is not universally the case. It is global mutable state that can hurt you, as revealed in core guideline I.2, avoid non-const global variables. If your global object is immutable, then it's merely a property of your program, like the gravitational constant, or pi. The point is that you know why globals are bad, for the reasons enumerated earlier. And you can decide when it is appropriate to bend that rule, with a full understanding of the technical debt that you're taking on.